Okay, we should be live. Welcome to another session from a while of a research channel on the assumptions of physics. Today we're going to try something new. We are actually going to try and see if we can start writing papers collaborative together in this setup and break ground in the way how we do research. The preamble is that we had published a paper on the unsuitability of Hilbert spaces to to describe physical state as a problem with the Hilbert spaces. They always imply that for any operator that it's unbounded, you are gonna have some states for which the expectation is not well defined, the value is not well defined. And worst of all, then you can have unitary transformation between states that are that have the value well defined and not well defined. And so then we can use this to create coordinate transformation that change things that are finite into things that are infinite and vice versa, and the unitary transformation that can change things from finite to infinite. And this would mean that whether a state is actually physically measurable would be essentially coordinate dependent, and that's why we wrote the paper. I don't know if actually the live is working or not. I'm a little bit concerned. Let me check that
I have
first.
I have it up on my phone and it's working.
Oh, okay, good. Thank you. Thank you for the
Yeah.
confirmation. Because after like a month that we haven't been doing things, of course, things started to break because nothing in software remains as it is after a few months of not using it. Okay, so that's that's our paper. And then we got a response from Professor Lemol. I think he's from Brazil, if I remember correctly. It was some South American country. I should check my stuff before saying things. So we have the links to both the paper and the response in in the notes. And he is from Brazil. Yes, I remember correct. And he actually had contacted me with his concerns. And again, it seemed to me like his main claim is that uh, observables should not change value doing a coordinate transformation, which again I find very confusing because if you do a translation, the position better change because you're doing a translation. And I tried to convince him that that would be the case and didn't see it going anywhere, so I basically stopped. But then he wrote a paper in the archive, which got published. And I just noticed today that in a note in the archive, he also says that he was rejected from the journal where we actually submitted the original paper, where actually it was accepted. And that's why the response is published in a different journal, Robbie. You asked me which journal we should publish this, and I said, well, you publish a response in the same journal where the article
Yeah.
was. And that led me to think, why is this response not on the original journal? Well, because in the original journal was rejected. And again, since the problem in the response is, from my perspective, not very interesting. I wasn't even going to write a reply. I'm busy with other things and so on. And so I said in our Discord, if there is anybody that wants to take a stab at this, all power to him. We're going to do it and so on. And Robbie here took the initiative and he wrote, so he did the research, basically finding essentially textbooks that show that how coordinate transformations are done, and what he's doing is not representative of that. And then he wrote the draft, and it took me a little bit by surprise because I was expecting that we just talk about things today. Instead, we probably are going to go through the response and finish the paper. And yesterday I sort of rushed to talk to the other writers of the original paper. One is Professor Cristina Aidala, my wife, and she's currently at CERN, and she's actually, right now, she's on a plane. She's coming back, and she also said that basically this is ready to be published. We just have a couple of things that needs to be, made better, but they're completely minor thing. The other author instead is so busy with other things and is stressed out with other things that he most likely just wants us to do it and go ahead and that's it because he doesn't have the time. Even if it was a trivial thing, he said, well, I should read the original paper and I don't have the time and blah, blah, blah. So, okay, so this is the whole preamble. I would just, Robbie, give it to you, and you tell us what you saw and everything.
Okay. And I did make that slideshow. Should I go off of that or just the
Yeah, you can do whatever you want. The floor is
Okay.
yours.
Okay, thank you. Yes, let me just navigate here. Okay, so we have our original paper and then a criticism. Here's just like a mathematical summary of the original. We have a state with well-defined expectation value for position. And then through a change of variables.
For position square, it's the variance.
Okay. Okay, yeah. And then through a change of variables, we get a state that is not well-defined for expectation value. And just for clarity, we're in the Hilbert space of square integrable functions. And then Novaldo Lemos, essentially his argument is that every unitary transformation is a change of basis. And as such, expectation values don't change under a change of basis. Like we expect, a change of basis doesn't change the system at all. It's just a different way of representing it. So intuitively, like we don't expect any physical quantity to change with a change of basis. But we will find some issue with this idea that every unitary transformation is a change of basis. Here is a excerpt from Shankar's Principle of Quantum Mechanics. And essentially he says that either we change the states of a Hilbert space or we change the operators. So yeah, this sentence here is pretty clear. It is clear that the same change would be effective if we left the vectors alone and subjected all the operators to the change with the unitary transformation. So yeah, these are two different ways of applying the same transformation. If we change the states, that's an active transformation. If we change the operators, that is a passive transformation. And then let's see what Lemos says.
Yeah, do you have exactly that? Perfect. Good. Yes.
Yeah. So a change of basis is carried out by changing the states and the operators with the unitary transformation, which is pretty straightforward. And here's also the reference he used was Messiah's quantum mechanics, and pretty much just echoes the same thing. So to be clear, we use unitary transformations to perform a change of basis, but this does not mean that they're the same thing. So that's really like the central disagreement between Gabriel's paper and Lemos's paper. Yeah, it's honestly not super interesting, just a very misconstrued argument with what a change of basis versus a unitary transformation is.
Yeah.
But really the clear distinction is in general with the transformation, we change the states or the operators, and in general, the unitary transformations do not preserve expectation values. But if we change both the states and the operators, we get the same system, and the expectation values are preserved.
Yeah.
This is kind of a simple example with spatial translation. Obviously, if we translate a state spatially, or if we move where we're observing it from, we expect a different expectation value for position, which is very intuitive. That applies to classical mechanics and quantum mechanics. And then if we were so if we transform the state and then we apply the inverse transformation to the coordinate system or the observables, then we get back to the original system, but in a different representation. And at first I was kind of confused about this because I was thinking if we move the state and then also move the coordinate grid, then we'll just translate it twice. But I think we have to do the inverse transformation for one of them.
Correct. That's exactly how it works. Yeah.
Okay, and this was another one of his points that I wanted to discuss with you a little bit. I don't know if we will address this in the paper, but yeah, it's not super complicated, just a bad representation of what a unitary transformation is on Manos's part. Well, yeah, I hope that's pretty clear. I don't know. Should we take a look at the paper now, or what do you think?
I mean, up to you. What is it that you wanted to discuss on the time evolution? We can finish that if you want.
Okay, yeah. So
we're not going to put it in the paper because I think that just showing what he's doing and showing that he contradicts what the textbook says for coordinate transformations, I think that's it. I mean, there is nothing to.
Well, he says there's a contradiction with the commutator here, and honestly, I haven't looked at this very closely, but I guess
I mean, he goes into a whole other series of arguments, but I think we just concentrate on one and I think that's basically it, because all the others are children of to me the main. I mean, we can go through his paper sort of since you probably have it fresher than me. You can go section by section and say, okay, here is saying this, here is saying this, because I just want to make sure. This is what happens a lot of the time when people write response, that they write a response to what they think is in the paper instead of what is actually in the paper. And sometimes also you as a writer, you have an idea of what you have in the paper, which is not exactly what you wrote. So we just need to be sure that that's. So maybe we can go to his original paper and let's get to the main sections that he has. In the text, if you remember where are the pieces that are the important pieces that we have to respond to.
Well, first of all, the first sentence in the abstract, there's no disagreement that states of a quantum system are vectors in Hilbert space. So some of the language was kind of concerning and kind of misconstrued the original paper.
Yeah. I mean, the first sentence is great because, first of all, quantum states are not vectors. Vectors, are represented as vectors, but they're not even represented as vectors because really they're represented as rays of the Hilbert space. So it's so much fun. Anyway.
And so yeah, the main objection is kind of what we went over.
Okay, the mirror is represented change in variables. So the Adami physical is a unitary transformation. You're going to look and map with okay.
Yeah, so a change of variables, which is a unitary transformation representing a change of basis. This is probably the biggest disagreement we have. A change of variables, well, you could use it as a change of basis if you transform the states and the operators.
Correct, yeah.
if we want to do something like a change of reference frame or a spatial translation, we do not want to do change of basis. We want to transform the system physically, and
Yeah.
we will get different expectation values for various properties. Um, Another sentence that kind of echoes the same thing. Every time independent unitary transformation in the Hilbert space is a
So
change of
this is what
basis.
I don't understand. Like if he says that that's the case, then how do you have laws of evolution? Because you're saying like it's so inconsistent.
Yeah, I feel like maybe he's arguing that only time dependent unitary transformations can like change the system or something like that.
Which means harmonic oscillators never change anything, right? Because
Mhm.
like it's
And it would also kind of imply like if you have a bunch of observers at different positions, they would all see the same thing for like position of
yeah,
a system when they're
and nothing changes in time, and yes,
yeah,
it's a very static universe. Okay,
yeah.
so now under a change of basis carried out by Real, the state vectors are transformed as that. So here's the problem: is that like is there a pay something that where he really claimed these are the rules for change of coordinates? Because here he's retrenching and he always says uh, uh, a change of bases. Okay.
Yeah, I think he kind of I mean in the this earlier part, he just says change of variables is a change of basis, and then he just sticks with the language change of basis.
Yeah,
Doesn't
exactly.
affect
Yeah,
expectation
because I
values.
guess in his head they're the same thing, right?
Mhm.
That's I don't think we're ever going to be able to tell him, no, look, they're two distinct things.
Well, hopefully our paper can convince him.
No, it's never going to happen. It's never going to happen, Robbie. I'm sorry this is the problem with this field is that people they become convinced of something and then that's it. I mean, he's not a young guy, right? Like it can't be that this is the first time where this showed up. He wrote books, right? So
And then I guess he goes through the mathematics of showing that in a change of basis, um, this
yeah,
is
yeah,
the
this is all
expectation.
filler. There's no more content here.
Yeah, expectation. We should get different thing, or we should get the same thing for
Yeah.
expectation. Um, yeah, unitary transformation. And so he's trying to say,
Okay, okay, let's try to find out how the position. So,
yeah, he gets a different, or he gets an expression for what he thinks the position operator should become.
right.
Um,
So if we can use that, so
yeah,
that's not really so interesting. Like go down at yeah that part. Oh, too much. A little bit above. Okay. So for the position x in reverse is that x tilde. I don't even know what he's doing here because he's apply. Okay. I thought that phi was the transformed operator.
X tilde, no?
Ah, so the tilde is the transformed operator,
Yeah,
and
X
the
in the
phi
Y
is the thing
representation.
multiplied by x. I see.
Mm.
Again, I've never seen it written like that. Yeah, okay, no,
Um,
we can't use these. These are not one to what Shankar does. And this is the same thing. We are already at page 5. It's still the same argument. There is nothing else that it's being.
Yeah. Yeah, I guess he's just going through change of basis for this particular example. Um, but yeah, he gets that expectation for the transform system should be the same as the original
Okay,
system.
okay, okay. There is another conceivable way to understand the origin of unsound conclusion. The author have interpreted change of variables as a unitary transformation that changes state vectors by these observers alone, as it were the result of a time evolution of squaring. I mean, that's what we should close quote. It's not our confusion. It's how it is.
Oh yeah, yeah, I see what you're saying. And then so yeah, this is getting to the part that the last slide I had. Um, I think he's trying to show so he has the general form for a physically reasonable Hamiltonian, and then I think he's trying to show that this makes a contradiction with the commutator here, where this should be zero or like a delta Dirac or something. You see what I'm saying?
Oh Lord, what is he doing here? Okay, first of all, there should be a mass. Okay, the mass, we were, of course, we're going to ignore masses because. Okay, so he goes, okay, the consequence. No, no, you can't write that. What? Oh,
Yeah. Could you explain what he's trying to do here a little bit more?
I
Just
have no idea what he's trying to do. I just see a commutator with between x and x dot. It's just, oh Lord. Okay, let me see. I have to go a little bit back up.
okay.
Let's see. In the Schrödinger picture, observables are fixed in time. Yes. So the only conceptually sensible interpretation of equation 17 is that time evolution is that it represents the dynamical evolution of the position operating in the Heisenberg equation, namely cosine f of x.
And then I think f of x is yeah, yeah, right.
Okay, fair enough, because you can't write the tangent. For some unknown reason, he doesn't like that function. Where x is a position, it just happens, however, that the supposed time evolution cannot be a time evolution in the Heisenberg picture generated by any physically reasonable one dimension. Of course, he can't take that form. Of course. What's the point?
Do we I mean does every Hamiltonian need to look like this?
No, absolutely not. Absolutely not.
Um, do you have would do you have like a good example for something that's different maybe?
And I personally don't have them, but it's in the general theory of quantum mechanics just tells you that
Yeah.
that has to be like the only requirement you typically have on a Hamiltonian that has a lower bound,
Hmm.
right? That you typically don't want to have a Hamiltonian that can go down to infinity because I don't even remember why. Oh no, this is where I show my ignorance. I don't recall why Hamiltonian needs to have a lower bound. Something bad happens, but I do not remember what it is.
Like negative energy or something?
Yeah, but I mean, in classical mechanics, I mean, you can do it and nothing really bad happens. But in quantum
Hmm.
mechanics, let me check, quite frankly. Let's see. Why do Hamiltonians need a stability condition of thermodynamics? Yes. So yes, there is one that comes from thermodynamics. But isn't one also on the dynamics, or is just thermodynamics? Because if it's just thermodynamics, then you could have also a Hamiltonian that doesn't have a lower bound. To
Uh,
have a lower bound. Or bounded from below, I guess. That's oh no, it's not. It's the same bound. Hamiltonian that are unbounded from below lead to instabilities of the physical system in question. Mathematically, it simply just means that the Hamiltonian or Crowdin energy can take arbitrary negative value. It has no lower bound. There are different ways to look at this problem. Let's see. Stack exchange. Let's see if there is a things that change if you consider interacting theory. Suppose you have a system S1 with a Hamiltonian. Okay, so yeah, you're gonna have problems when you have interactions, basically.
okay.
Uh,
Well,
so
maybe that would be a good point, like counterpoint for the papers. I guess showing that the Hamiltonian doesn't need to
I,
follow.
I wouldn't because it's not. This is again, it's just a child of thinking that everything has to, look the same in as that in all coordinates. I mean,
Mm,
think about it. Going on a rotating frame. On a rotating
mhm,
frame, the thing is not gonna be that. It's gonna be something else. Right. The classical gravitational potential is not bounded from below. Exactly, right? So, again, it's what I found in the answer is basically a problem with interacting theory, which actually is a problem also in classical mechanics, that
mm,
you can have things that escape with like with infinite, like they go at infinity, infinite time if you find interesting initial conditions and stuff like that. Uh, so yeah, so I think that the problem is that if you just have one thing with one potential that it's not bounded from below, it's not a problem. But if you start doing something serious with it, you're going to end up with problems. But then again,
mm,
it's irrelevant to the discussion at hand, quite frankly. It doesn't matter.
mm.
So his problem is that when you do a Fourier transformation, the Hamiltonian changes form. But yes, that's exactly what happens. It's in
Mm.
classical mechanics, it's the same thing. I don't know what he's thinking. Also, even worse, relativistically, the Hamiltonian is not an invariant, is the time component of a covector. And so, it can't change the same. That's kind of why Lagrangian mechanics is so nice, because the Lagrangian itself is invariant. And so when you look at symmetries of a Lagrangian, you really are looking at symmetries of the system. And
Mm.
it's a lot harder to do it for the Hamiltonians. Uh, so
Okay.
yeah, so I wouldn't respond to this part of the paper. I think uh, it's just the same. I mean, he basically claimed, right? So if we go back before, he said that our confusion is the fact that we are only changing the state, right?
Yeah, yeah.
He claims it. So I would just say, have interpreted the change of variable as a unit transformation that changes the state vector by leaving the observable alone. Yes, that's exactly how it works, and see the textbook.
And so this sentence here is not true because if you want to do a spatial translation, you don't need to prove that a
What does it
translation
mean physically?
operator.
So this is even so we are basically like the whole paper was to find the subclass of states that are physically meaningful. And now it's basically saying, well, not all Hamiltonians are physically reasonable. And it doesn't even say what that class of Hamiltonian is. I'm not going to reply to this. It's just, it's like, there is something called the first rule of debate.
Uh,
And I'm not going to say live what it is. I can tell you later what it means. Okay,
um,
so
Okay,
Let me,
maybe.
there's a comment on the channel. Let me read. What I got out of the paper when I read it back when it was new was something like he's saying it's only a problem if it's a problem in non-coordinate frames or something. Well, I don't know. Like he states that we're doing the coordinate transformation wrong. So I would say that the author has interpreted, and I would take this like highlights or something. Keep it so that we're gonna put it in the response. Because
Mhm.
again, I like when a response takes the thing from the paper, says the person is saying this. And this is what the other thing says, right? So that makes it clear. Like he thinks we're making a mistake because we're only applying the unitary transformation on the vectors. Like he thinks this is a mistake.
Yeah. Well, I just want to reiterate this point. This transformation presented in the original paper,
Mhm.
we can interpret this as like either we're like accelerating the system away from the observer or the observer is like accelerating away from the system, something
Right.
like that.
What you're doing, you're squishing the space or stretching the space.
Mhm.
That's basically your idea. So the passive transformation is let's see. Now I have to understand which one is stretching and which one. Well, I don't know which one is going to be. But in the active transformation, you're basically taking the things and moving them away,
Mhm.
right? In the passive transformation, the things are staying where they are, but you squish your reference frame.
Mhm.
Yeah, that's basically what's happening.
Yeah. Well, so you said the expectation of it's x squared.
Yes, it's a square that changes. Yes.
Doesn't this also go to infinity? Because it's like,
No, it is always centered at zero, right?
but
So these
it'd be
are
like the integral of like 1 over x.
it would be the integral of x squared with probability density.
Because if we get like 1 over x squared from this times its conjugate and then multiply by x, that would go like 1 over x.
Right.
And then wouldn't that integral diverge?
Yes, but you have the symmetry,
Okay.
right? It's a bell shaped curve, and so it's even or odd. It's even, right? Yes, it's even.
Okay.
Right,
So
it's a
you,
symmetric along the zero, right? So if you imagine to make the integral starting from zero and then make it in a range that's symmetric in both sides, the thing is going to converge to zero.
okay. Um, yeah,
So
I
if you
guess.
if you cut that thing off, right, and you do it only on one side, then
Mhm.
yes, you would have the expectation, but then the expectation wouldn't be zero at the beginning, it would be some positive number, and then it goes to infinity.
Yeah. Okay, I gotcha. Okay, yeah, I see it. Because you're multiplying by x and then it would like flip. It'd become negative on the negative side of the real line.
Yeah, yeah,
Yeah. Okay, I got that.
yeah.
Yeah, well, I think we've laid out the big disagreement. Um, I guess where should we go from here? I have a kind of some more general questions about quantum mechanics as well.
So we
I
can
don't.
do all that. Then what I want to do then is start editing the paper together
Okay.
and look at the few things that need to be finalized. If we can do
Mhm.
it together here live, great. Otherwise, we just put notes and either you do it later and
Yeah.
like
Okay.
the thing that needs to be done was that I saw was a sentence at the beginning that needs to be introduce our paper that you don't have because you there like you go directly the central charge in Lemos paper. Well,
Yeah.
we need to first say what is it that we're doing, and
Yeah.
probably we don't need the title introduction because it's just gonna be that. In
Yeah,
fact,
no.
if there is a way to submit this as a letter to the editor instead of a new paper, I think it would make more sense. But we'll see what happens. Then probably we want to get more of the quotes, like in the same way that you had beautifully like quoted Shankar. I would like to quote him with the same exact words and formatting, including that sentence that we identified that makes it clear that that's the source of the disagreement. And I think that that was basically it. I don't recall there was anything else.
Okay. Um,
So let's start with your questions. So we do more useful things.
yeah. Maybe I'll stop sharing so people don't have to look at my Google Sheets. Um, so yeah, this first one just reiterating active versus passive transformations. Active, we, for example, move the system. Passive, we move the observer.
Yeah.
And then with time evolution, so the Schrodinger picture is the active transformation and Heisenberg is passive.
Yes.
So if we could apply a time transformation to the states in the Schrodinger picture, and then if we apply the inverse time translation to the operators, it would constitute a change of basis.
Yeah.
But is there any reason we would do that?
No.
Um,
Again, the other thing that it's weird, especially in quantum mechanics, is saying that, let's say, a change of position, a change of coordinates is a coordinate transformation because there is no coordinate for position. Like there is no, sorry, there is no basis for position. Like
yeah.
the continuous operator, the operators with a continuous spectra do not have eigenvalue, eigenstates. They don't give you a basis.
Yeah.
So even thinking about all sort of unitary transformation related to observables as changes of changes of basis is just doesn't work. Like
Yeah. But we do like we don't have eigenstates for the position, but we can use like eigenstates of um the harmonic oscillator as to span the space.
Right, but then that would be sort of a change of basis, of the energy, not of
Mm,
right of the position, right?
mm,
When we talk about change of coordinates, we are specifically singling out the position operator, right? There is no change of coordinates with momentum or energy, or no, the coordinates are defined by the position.
mm. Yeah,
So I'll give you an example. Suppose that we are, we're talking about spin, right? And then you want to change to make a change of variable, right? A change of variable means changing the triple of the sx, xy, sz, right? And again, of course, it's going to give you a unit transformation, but it's you still think that as a coordinate transformation because you think as those forming a vector in physical space. So there is no coordinate transformation without a position. And
yeah.
let's see, suppose that I had, I don't know if it would make sense to make, right, so suppose that you had some type of quantized system, but you don't know the position in space or anything. You just know that there is a ladder operator that goes up and down. And you
Mhm.
don't know how that ladder operator relates to position and momentum. You're not going to be able to talk about a change of coordinates because you have no idea what's going on. You just have your ladder operator. So
Yeah. Yeah, I keep bumping into the idea that the position operator is problematic.
mm,
Um, and that is another kind of a question I had. Because so in Hilbert spaces, like we define operators on a Hilbert space,
Mhm.
but Hilbert space by itself, just vectors and inner products, there is no, as far as I see, there is no room to get something like an infinite expectation value
Right.
unless you define operators on top of it.
So you can, so if you have a Hilbert space, even L square, what you can do is just consider all the bounded operator, and then you can think of the something like the position as a limit of a sequence of bounded operator.
Mhm.
Like you basically have the position you're putting cutoffs, and you make the cutoff, bigger and bigger and bigger. So in principle, you do not need, uh, uh, let's say, unbounded operator to explore the space because you have all the bounded one,
Mhm.
right? The issue is that then you are gonna be able to find again, you're gonna have vectors, states for which the expectation of a position is not well defined, which means can be infinite, can be completely undefined because it doesn't converge.
Mhm.
And then you're going to have another unbounded operator, right? For which the expectation is totally, sorry, another bounded operation for that, for which that is absolutely fine.
Mhm.
So, like for any operator, right? Sorry, for any vector, you can do the projection on that vector as an operator. So it's going to be the operator that gives you one if you have that vectors and gives you zero if it's any orthogonal vector. And
Mhm.
then, everything else is going to be a linear combination of those two things. And that's always well defined. And, in principle, projections are measurements, preparations, whatever you want to call it. So again, if you want to say, oh, all the projections are measurements, you end up with the same problem because now you can project into something that has an undefined expectation value of position, of energy, or whatever you want. I mean,
Proj- is
it would
and
be convenient to be able to do it. Go ahead.
projection is projection is Hermitian.
Yeah, yeah, right. Because any projector operator is going to have eigenvalue ones or zeros,
Mm.
right? So they're all positive eigenvalues. Or, well, non-negative and real. That's I mean, real. That's what I wanted to say.
Mm. I guess my point is you don't get any infinities in Hilbert space until you define unbounded operators on them.
Well, you are going to have an infinity on the basis, right?
But I mean for expectation values.
The expectation values are only defined on the Hermitian operators.
Mhm. Yeah.
So
Um,
as soon as you start defining operation value on Hermitian operators, you have to define Hermitian operators, and then if your space is infinite dimensional, you can have unbounded operators, but then those are not going to be defined on the
yeah,
whole.
on the whole space. Um, so I guess it's maybe just semantics. Like Hilbert spaces, just vectors and inner products, no issue. But then also you can't like we need observables to have a physical theory. Um, but maybe the title that I would like instead would be the unphysicality of the position operator, for
No,
instance.
because so if I give you a Hilbert space, you're not going to be able to define to map every single element of the Hilbert space to something physical.
But if physicality, if we're using, if our requisite for physicality is like well-defined expectation value for
No, no.
position, and
If you remember, there is a section in which we define it, and we basically say something is physical if you can map all the elements to a system, a physical object that is realizable, and you can go back and forth.
Yeah.
Right. So the definition captures and only capture a physical aspect of the system.
Yeah.
So now
Yeah.
for Hilbert spaces to be physical, it means that every axiom that is part of the definition of a Hilbert space need to translate to a physical property, and that all the elements in the Hilbert space must correspond one-to-one with a set of physical well-posed object. You need to be able to do that. That's how we define it.
Okay, so say we were able to set up an experiment where we start with a Gaussian state, like the first wave function you provide, and then we have a detector that we move in a way that is synonymous with the change of variables in the paper. Is this paper making an experimental prediction that would go against quantum mechanics?
The claim here is that in one coordinate, you are going to have a finite expectation. And the other coordinate, you're going to have an infinite expectation.
So yeah,
Therefore, wait. Therefore, when you gather your statistics in one reference frame, your statistics are going to converge. And when you gather statistics in the other reference frame, your statistics are not going to converge.
So if we set this up experimentally, what would
the point is that you can't.
Yeah, but we could, like, feasibly we could.
No, the point is that you physically couldn't.
But we could have.
It's just a thought experiment, because it's not an actual prediction. It's an argument that tells you that the prediction would go beyond what you can physically measure. So it can't even be disproved because you can't set up the experiment.
So we couldn't set up a system and then a moving detector that is looking at the position of the system.
Yeah, but this is not a moving detector. It's something that stretches all space at infinity. Just think about it as an active transformation, right? What would you need to do as an active transformation? You would need to do something that everything is stretched out or compressed in, and the farther you go, the more stretched out you are.
Yeah.
Okay? Exponentially faster. You're not going to be able to do it. Like it's not.
But for maybe a short amount of time, it would. Well, so am I wrong in thinking that it could be you could accelerate the system in an appropriate way to reproduce
but you have
the
to
change
accelerate
of variables?
every part of the system at each point differently, and you have to do it going to infinity. And as you go farther, you're going to have to accelerate the system faster and faster exponentially.
Yeah. Okay. So it wouldn't just be the whole system moving together. No. Like each piece would have to do different things.
Yeah.
Okay.
If you're moving everything together, that's just a translation. It's not an issue.
But if it's accelerating and it's a non-inertial change of reference frame.
Yeah, these are all going to be non-inertial. Reference changes. Yes.
Okay. Yeah, I guess that.
So the only response that we got that was a little bit of pushback that kind of made sense was in a reviewer basically said, well, but this can happen in classical mechanics as well. And it's true. If you have a classical distribution, you can make these same coordinate transformations and you go from finite expectation to infinite expectation. The problem is that then the reviewer said, well, if it happens in classical mechanics, then it's okay.
Yeah.
It's okay if it happens in quantum mechanics. And the problem is, one, there is a significant difference between classical mechanics and quantum mechanics. that in classical mechanics, you can have a distribution with finite support, with compact support in both position and momentum. And as long as you have a distribution that it's a compact support in all the variables, no matter what coordinate transformation you do, all the expectations are going to be finite because you have a maximum, a maximum and a minimum for all the variables. So you can't go to infinity.
Okay.
And therefore, you can just say, well, in classical mechanics, the real physical things are the compact supports, which also makes sense. You can say, well, the Gaussian is an idealization. We never go to infinity. You can say these things. There is a cutoff, and that's it. And then your cutoff is this, making the compact support. And so you don't have a problem, a significant problem with the theory. In quantum mechanics, there is a problem because if you have a compact support on position, and this is we write in the paper because I thought about this. If you have compact support on position, you have non-compact support on momentum. And same thing, if you have compact support on momentum, you don't have compact support on position.
And that's just like the uncertainty principle?
Yes, it's because one is the Fourier transform or the other. And if you have a function with compact support and you do the Fourier transform, you get an entire function. An entire function is defined on the full thing. It does not have compact support. This, if you go through the paper, we give a citation because also I don't know exactly the definition of an entire function is it's a complicated thing, and I didn't want to understand. The point is that the result is there. If you look at math textbooks, that's the result. So that's why you can't do it.
Okay.
But I still think there might be a more of a random problem even in classical mechanics. I do think that there must be something where you basically need to say, look, not all coordinate transformation actually make physical sense. Like these things that go to infinity, or something that takes infinite space and transform it into finite space. Because you can have a transformation like that. If you just take the arctangent, right? It's a bijective function from a finite space to the tangent, right? It has a compact domain, and then it goes to infinity, right? So you can have something that stretches, that you do the arctangent, you take something infinite, and you make it now finite in terms of support, and finite in terms of distance, and that I physically I don't think that it's gonna screw up a lot of other things. Like the definition of entropy probably is gonna be screwed up if you try to do things like that, because now you have if you think of volumes of space as defining entropy, good luck what happens as you go closer to the infinity. Like the things are going to have higher. So there are other things in the math that are probably not in the math, in the physics, that are probably bad. And so my reaction to you can do these things in the classical mechanics is you most likely are going to have some problems in classical mechanics as well. And so if we maybe like the resolution is when you describe the principle of relativity, even in classical mechanics, you have to put some condition that not all coordinate transformations are good. Like some read don't make sense.
Okay.
And you should avoid them. So.
Yeah. Well, yeah, it's a lot to think about. But I think, I guess the central point still remains Lemos misconstrues something pretty fundamental, we think. And but yeah, I'm interested to hear about your maybe unphysicality of coordinate transformations or restriction of coordinate transformations. Maybe would that remedy the unphysicality that you point out in the first paper?
So that's kind of I'm trying to so I think that's the solution. To me, I feel that that's the solution. I just don't know exactly how it's justified, and I don't know how it generalizes. So for Schwartz spaces, right, you're basically going to say, okay, all the expectation of pole polynomial position momentum, they're the things that are important because those are what essentially give you a complete set of quantities that fully identify the states, and those you need to be able to measure, and so that's good. And my hunch is that that's gonna be also the correct groups of generators, right? So you need to be able to both coordinate transformations and the time evolution, right? Needs to be defined. What is the correct group of transformation? And you can imagine of restricting the group of transformation by restricting the groups of generators. And then you say, oh, let's think that the group of generators are the polynomials, right? And now whenever you make a coordinate transformation, all your generators are still going to be polynomials because you're going to make a polynomial transformation on a set of polynomial, you're going to remain in the group. And so that might be the thing that you say, like in one, in one move, you sort of constrain all these sets, right? Because at the end of the day, active transformation are dual to passive transformations. So if we restrict the passive transformation, the coordinate transformation, we most likely need to restrict the active transformation as well. And so it makes sense that the polynomial is a good group because like if you imagine you're going to have constant transformations which are like completely useless, then you're going to have linear transformations, good. And once you start having once you start going beyond that, you are going to get the like once you start allowing for the quadratic, then with the quadratic you make the quadratic of the quadratic, right? And then you can make all the polynomials essentially. So it would make sense that the correct group is the polynomial because it's like the linear is too small, right? Because that would be only inertial frame stuff like that. So you need a little bit more, but then once you take more, you get the whole group of the polynomials. And then if you go beyond the polynomials, you start having these problems because you're going to have things that fall down. You can make things fall down faster or slower than a polynomial if you introduce other things. So, but I don't know, right? I don't have any confirmation. These are just thoughts and words. I don't know if it makes a consistent theory. And then once you start having a field theory, there might be other things, right? Because it's not just Fourier transformation; it's transformation of the fields. And so I have no idea what is the correct group there. So yeah, so finite order polynomial stuff is fine, but exponential stuff is not. Yeah, that would be the my hunch. But again, it's just a hunch. It's not. I don't have a solution. Quite frankly, I'd like for somebody who has more intuition at the mathematical level on group theory to help me figure out what is the correct group, or even figuring out whether this group theoretic way of looking at things is actually does actually make sense, because maybe it doesn't. I have no idea.
So if I understand correctly, you want to restrict the set of states and the possible coordinate transformations, like both, right?
Yeah, I think you can't restrict one without restricting the other.
Okay, and then because you restrict coordinate transformations, you basically also restrict active transformations, generators.
Correct. Because
So
you can't
would
restrict
also,
one without restricting the other. Yeah.
yes, and then basically we would also have, I guess, if you want to look at the state and momentum space, we will also have like a smaller space, similar to position space.
Yeah, they go together. Like once you restrict with the polynomials, you're restricting both polynomials of position and momentum.
So, but that means like it's not the dual space of the Schwartz space, like the tempered distributions for the momenta. But like if I want to define, like if I can a Fourier transform a Schwartz space and get like a Schwartz space and momentum space.
Yeah,
Does that
yeah,
make
that's what
sense?
Schwartz space is closed under Fourier transform.
Okay, okay. So this is what we expect, basically.
Yeah.
Like all the generators are the Schwartz
Yeah.
polynomials and momenta.
Yeah.
Okay, okay. That makes
So
sense.
what happens to the people doing mathematics, which I think is the problem, is that once you have a linear space, they think of the dual as the space of good operators or valid operators. And in our case, I don't think I don't think that's the case. So if I have the Schwartz space, right, I want the space of operators to be the polynomial position of momentum, which is not the dual of the Schwartz space, because the dual of Schwartz space would include, for example, delta Dirac's in position and momentum. But those things, here's the issue. Those things are not physical because you still have there are limits, right? They're not things that you actually go and implement directly. And they don't add any information because once you have the expectation of all the polynomials, you have reconstructed the state. And so all those other things are not are extra things. They're not they're not the things that are going to define my state. And so what I think is interesting is that the and then the other thing is that they do this because when they typically define the inner product, they define it as with the duality. So the inner product is between an element and an element in the dual. But that's not what we want to do in physics, because in physics the inner product is between two states. So it has to be between two elements of the same vector space and not the element and the dual. So the whole sort of attention of what is the dual, I think it's the thing that is leading you in the part that is not physical. It's completely okay to say, for example, I have the Schwartz space, I have an inner product on the Schwartz space. And the operators that I care are the polynomial position momentum, which happens to be the things that are finite, that have finite expectation in that space, and they're well defined, and they chart everything. And in fact, they generate the topology, and leave it at that. Like you don't need the everything.
Should we go to the paper now?
Yes. So Cram, I was asking, so the rigged Hilbert space basically does that. You have the Hilbert space, and then you take something like a Hamiltonian, and you find the space of the states where the Hamiltonian has finite expectation, right? And that becomes your smaller space where you do things, and then you're going to have a dual, right? And so the rigged Hilbert space is this triple. Like you have the Hilbert space, the smaller space of things that are actually make physical sense, and the bigger space of the duals, which are going to have the delta Diracs and stuff like that. But it's not a solution of the physical problem. I mean, it's more of a clarification of the mathematical objects, but you still have too many things. You still have to tell me what each element is. And while you can sort of say that the smaller space is the space of physical states because the Hamiltonian is defined, whatever operator you choose are defined, and the dual is the space of operator on that. The Hilbert space that sits in the middle is neither, and it's still not physical, because if you can make the identification for those two things, the thing in the middle is there doing nothing. So you should throw it out and then figure out how you're actually constraining the space. And if you're constraining the space through operators, you just say that I have the vector space of an inner product vector space, complex vector space, where these operators are defined, which is similar, for example, what the construction that people do in algebraic geometry, where they start with a C star algebra on the observable. You start with the observables, and then you define the space as the thing, the linear functional of the observables. So you start with the observables, and the states are things that you can ask what's the value of the observables, right? And I don't know then why they extend to the full Hilbert space, but that I never quite understood. But anyway, yeah, let's go through the paper. Should I share? Do I have edit ability?
Yeah, I think you
Let
should.
me see. I think I need to go to your email to get the link. And I think right. Okay, so let's do it. Let me take this out by itself so I don't get distracted, and then I can, no, how do I close this? Okay, maybe oh, there you go. This is the button, and then I can share this one. Right. There you go. Let's see. I hope this is going to be readable somewhat through the live.
Yeah,
Okay.
it looks good to me.
Okay, so I would just keep the title as you had before, response to the title, and that's it.
Yeah.
Yeah, there is the abstract, and so and you also don't put the name in. I don't know if we put the name here. There's another case of our paper that says the future central that a state with an expectation value for a position can be mapped to a state with an infinite expectation value by a change of variables, by conflating change of variable with change of base in quantum mechanics, and you like that expectation values are invariant under the change of variables. In the present work, we prefer the distinction between change of variable and change of basic and rebut. Okay. So here we need, so first let me see what, okay, so we remove introduction because there's basically nothing.
Yeah.
And let me just put this here. I can basically say this notes to be removed, and that's so I do Control S to be yes. Okay, so here we need first to introduce our paper, introduce the result of our paper, of our original paper. The central charge is that change of variables is unitary representing. Okay, so the way the central charge in this paper is that a change of variable is a unitary transformation representing a change of basis. Given a unitary, so if we can make this with his own words, that would be better.
Okay. Yeah, I think I have a good quote from you.
And then so this unfortunately he doesn't quite write it like this, right?
Yeah, here,
Because,
should I just paste it in? Maybe up here. We got an extra 2 in here. Are you seeing what I'm doing?
yeah.
Okay. Okay, is that psi? Yeah, that's psi.
Yeah, I would use the other thing that so I would start with that sentence that we highlighted before.
Oh, about the Hamiltonian?
Oh no, about we misidentified the fact that we are only transforming the state and so I would start with that. So let's put all the pieces in my views. There's another change of value, which is the unit transformation with change of the state of which your expectation of so we are going to recap this part in our own word when we introduce the original paper. Right? We don't need him representing what we did in our original paper. We need his quote to tell us what we did wrong. So that quote that I told you to highlight, that I need that.
There is another conceivable way to understand the origin
Yeah.
of the unsound conclusion. You see that?
Yep.
Is this what you're thinking?
Yes, and then we can do this and
Okay, I see what you're saying.
yeah. So
And I think I have the quote where he says every time independent.
yeah, I would really leave the time stuff completely out.
Okay.
I wouldn't even touch that
But wait,
because
'cause-
this already tells us what the thing is. You interpret the change of value as a unit transformation that changes the state vectors by leaving absence around.
but him saying every time independent unitary transformation is a change of basis, don't we have issue with that statement?
I have issues with a lot of things, but the point is that when you're making a reply like this, it's much better to focus on one thing and make that one thing clear. That especially for this, because it doesn't really, like once we make this, right, this claim, and then we have this, right, that's it.
Yeah.
That I don't need to say anything else.
Yeah.
Like he says that we are interpreting this, and yes, we are.
Yeah.
But here's the thing, and then we're going to say, and he says that this is wrong, and he says that you should change both. And then we go and say, no, actually, in the literature, they do what we do. So at that point, I don't care what you're talking about, right? Like we are using change of coordinates in the way that the literature talks about it. He is not.
Yeah, he's just sticking to change of basis as.
Yeah. So, of course, if we apply with the things that we said in terms of change of basis, doesn't make any sense, but we weren't talking about change of basis. And we are using the language that is consistent with the literature. He is not. That's it. There is no other thing that I need to say. Like, as I said, this is not like, oh, well, there is this subcase, and yeah, it's tricky. No. Like, you're taking the thing that we did, that it follows some convention in the literature and saying some things, and then you are interpreting it completely different to say things that do not make sense in the context of the literature. So, right.
Yeah, I agree there. That'll be more straightforward.
And there is the core of the disagreement is that there is not, like, all the other things are consequences. So I don't care about talking about the consequences or reiterating the same point over and over like he did in 11 pages. Who cares? Like I don't have the time. So I'm trying to see, because the whole prose that you wrote like reads really well, right? So I want to make as fewer changes as possible, and hopefully I want to write it in your style, because what we don't want is have a paper where there is one sentence written by one guy, one other sentence written by one other guy, and so on, right? So it might even be that I tell you what I want to be said, and then you write it so that it
Hmm.
reads in the same style,
Okay.
right? Because
So yeah.
as I said, I was blown away. This to me would be ready to be published. I was especially impressed by the last paragraph, like because you
Mm,
struck the right balance of being sort of making the point, but making it in a neutral way that it doesn't come off as aggressive and so on. So
yeah.
yeah,
Yeah, I think we try to take the moral high ground here.
yes. And then in the video, I will take the I'll make a video and take the low. That
Yeah.
no, because this guy needs to be bashed, quite frankly. I'm not afraid of saying it live, but this is why, and I will say that in the live. I mean, it's the reason why the foundations of physics, especially the foundation of quantum mechanics, are a mess. It's because of this. You can't
Mm,
have like reason conversation at a high level. You're always rediscussing things that have been already settled 70 years ago. Jeez. You're not gonna make progress with that. Anyway, taking too much time. Let's be tactical. So I don't think I want this.
yeah.
The only thing that I want is to make this sentence basically be in his own word. And so, given a unit transformation here, a change of basis is carried out by transforming states as such expectation values are invariant. Okay, so this we're using our own notation because, which is the notation that people use in the quantum mechanics, because what he's doing is it does not map well to the notation here. So we can't just lift his thing and put it here. Intuitively, we
Yeah.
expect the measurable property of the system to remain the same regardless of what basis we use. There is no dispute over this point. Rather, we found Lemon's fault to be conflating unit transformation with change of basis. He claims that every time. Okay, so maybe we should remove this as well. He claims that every time independent universal change of phase or unit transformation are used to perform changes of basis, they're more generally used to transform one physical system to another without. So maybe we should say, do this. Let me think, because maybe this could be an introduction for the next section actually. So that here we just state what his problem is, right?
Hmm.
And then here we use it to say, but this is what everybody does. If a system is displayed for observer from a change of state, we certainly expect some measure to change of instance of position. GFS. Okay, but this stands on itself. So a change of variable represented transformation system or a change of area does not preserve variable expectation value. General transformation is carried out in two ways, an accurate transformation is such as partial transformation. So here, the thing that we need to put here is that this is an example. So this we should do. It's going to be easy to change. As such, a special translation of the observer may create a displaced observer. This is well established in the literature. And again, I'll put this, you should rephrase it as you would.
Okay.
And then this is where we cite. And then, for example, in principle, and then also here we put cite. Right. So here is where you said that you found over 4 or 5 books that say the same thing.
Hmm.
We want to cite all those.
Yeah, and because some of them are just about like spatial translation, so maybe I could cite those in the previous sentence.
I think is okay. Or let's see, we could use or we could add it instead here. Like we could we could add something here that basically says what we do is what is done in the literature,
Mhm.
or is consistent with established literature. Literature.
Yeah, I was trying to find a reference from the textbook he cited too, but they don't, I'm not finding a section where Messiah clearly goes over like translation or anything. But maybe I could use the same reference for like the first paragraph, just talking about change of basis.
Sure, like I wouldn't worry about it because
Okay.
like we do not need to. So you typically cite something to establish the credibility of the point that you're trying to make.
Hmm.
We are not trying to establish credibility of his point. We accept it.
Hmm. Yeah.
So we don't need the citation. We need the citation when we're basically going to say, yeah, what we do is actually what the literature does.
Hmm. Okay. Um,
Okay, so
so
I just want to understand where we put this sentence. If we put it here to introduce, his. Okay, so the central, you have something like point of disagreement, like.
yeah, maybe after that.
So
Mhm.
even this paragraph, we might be able to get rid of it.
Mhm.
Because what we want to basically say, so we have this, and he thinks that we are making it wrong because this is how we should be doing it. And
Mhm.
then we basically say, no, this is what we. Okay, so introduce. So let me just take a step, and as I said, maybe you can reword it in a way that you would say it, but say the same thing, so that it seems the same thing.
Mhm.
In our original paper, and in fact, we have shown that the Hilbert spaces are problematic as they allow a change of coordinates that map states with finite expectations to ones with infinite expectations. Creating problems claimed claimed that Hilbert spaces are problematic because they allow.
And I was trying to stick with the language change of variables. Because that's, yeah, that's what I think you do say change of coordinates at some point in the original, but
Is there a difference between change of variables and change of coordinates?
um,
I don't know if we are consistent in our paper because for me,
yeah,
change of coordinates, change of frame, and change of variables are completely interchangeable. Change of coordinates versus change of variables.
I think mm, maybe I don't know, it's all just semantics. I think maybe in the way they're carried out, there may be some difference. Or, if you're doing, whether you're talking about doing a transformation or its inverse, something like that.
So let's see. There is a question on Stack Overchange in the map that basically say are the same thing. I could require by change of coordinates, but how I can apply a change of variables? The change of variables are also, in fact, the other guy says, I would call, the thing we called change of variables, I would have called change of coordinates. Okay, so a change of variables when you change your coordinates, you're actually changing the set of points in the plane you're integrating over, i.e. converting the integral over half disk to an integral over a rectangle, mean the usual. A change of variables will keep the same domain of integration, but change the differential form. Of course, they're eventually the same thing. Yeah, okay, it's the same thing. So if we want to just be consistent, just stick to change of variables, we just do change of variables. It doesn't make a difference. So in the original paper, we claim that that Hilbert spaces are problematic as they allow. Okay, and then Lemus argue we reached, and let me put an unsound conclusion as we have have and then what is this yellow line that is underlined?
It's like an AI auto suggestion
Oh, what?
thing.
Ah, geez. Okay.
I
So
I don't know how to turn it off.
yeah.
It's very annoying.
Oh, whoops. Happened. Did I? Tobias had disappeared. Okay. Okay. So I think that's it, right? Because now it goes back. It goes back to what he's saying, right? So we basically say, no, this is what we did in the original. They argues that we said because we're going to return or well, we can probably.
Maybe instead of central charge, you could say central like misconception, something like that. Or
Or basically, we should make the positive. Like first, we said what we did wrong, and now we would say he further argues that a change of variable is a unity transformation. Is given, and then we explain. Okay, so there is no dispute over. There is a dispute that this is how change of basis behave. So I would remove all this. I like making papers shorter. So this is, there you go. So we keep the text, but I'll because okay, so we have established here that this is what he thinks. So, okay. Then changes. Of bases and here where we cite.
One note I have, I don't think any of the references I found mention change of variables specifically. But change of variables is a unitary transformation. And then we have references that show how unitary transformations are carried
Yeah,
out.
active transformations. I mean, like can you talk about, so you say Shankar does not use the term change of variables.
Yeah, I don't think any of the references do.
Okay, in classical mechanics though, so relativity change of a variable. Jeez, I want. Okay, so let's do passive versus active transformations.
I mean, so I like in your original paper you have the appendices with proofs and stuff.
Yeah, I wasn't thinking that we would do something like
Yeah.
this for this. Also,
Would
because
you?
if we can make it a letter, it's a lot,
Yeah.
quicker to.
Or would it be feasible to have a short proof that change of variables is a unitary transformation?
It's too basic. It's such an established thing in the literature. I
Yeah.
just need to show it. That's it. It's not a.
Mhm.
So this all implies that we are doing change of coordinates. I mean, this is the thing. So, okay. So if you can find using two types, I mean, geometric transformation, like measure coordinates. Oh, we were calling them change of variables. Let me see. Change of bases. Variable, no. Change. Okay, so maybe we change very. So we could go back to his word and say that this is called an active transformation.
Yeah, he does. I remember he says active transformation.
Does he say that?
Um,
Because the Shankar calls it.
yeah, here, let me paste this in. Because it contradicts Shankar's quote. I'll just paste it in the top again. Because he said it changes vectors and operators, which contradicts Shankar.
Any change of basis, a change of presentation was an active transformation of the Hilbert series that change spectrism. Oh, okay. Even better. Okay, so maybe we want to structure. Okay, there you go. And then side. But then I would put Shankar's stuff right here. But frankly, I don't even know if we need anything else. I mean, we let Shankar do the work for us.
Yeah, slam dunk.
So in original paper we claim that Lemos argues that we reach an unsound conclusion as we interpret the change of variable as a unitary transformation that changes state vectors but leaves the observers alone. He further argues that a change of variable is a unit transformation represented a change of basis given a unit transformation in two respects here. There's no this change variable. Lemos further claims. So maybe we should put this together with this. And we had something else. You had something else, another quote that basically said that that the changes of variables are unitary transformations, right?
Yeah.
So let's use that here. Where do we have it here or?
Right, let me double check.
Okay, so this we used, and this we used, so we don't need these. You had the quote before that he basically says, "Oh yeah, there."
One.
So. I don't know if it's just better, maybe here we don't put the quotation because it's just a mess. Change of variable as a unitary transformation representation.
Okay, but because you start with a summary of the original paper, I think
Yes.
that the quote I just pasted in would be appropriate after
This
that
one?
sentence. Yeah, because it's like the original paper finds problems, and then Lemos claims that we can't.
Okay, good. Like, tell me that what I'm doing wrong. Good. So as I said, it's better if it reads like what you would do.
Hmm.
So how do you want to introduce it?
Um, so we claim they're problematic, and then Lemos says, I'm not sure how I say it, like problematic. Like Lemos refutes this point.
So you had something. I changed your text so much.
Um,
We don't have the history. Whatever.
like, Lemos refutes our central argument. Um, because the quotation is him rephrasing what you did, but
Yeah.
but then he also his own statement that change of variables is a unitary transformation
Yeah.
is his quote. Um,
Do we need this or we already said it? He says it, right?
yeah, I'm not sure, but I think we do. We want the statement that a change of variables is a unitary transformation,
Okay.
but we have issue with the representing a change of basis.
Okay, that's sorry. So you want to keep this? Let's do it like this. You work on this paragraph,
Hmm.
on the whole thing, and I'll work on the beginning of the next one.
Okay. Yeah, and I feel like it's a little easier for me to just do this on my
Yeah.
own and
Uh,
um
you want to do it like later? We just finish up all the other things and then you take it, or you want to do it right now? Up to
yeah,
you.
I kind of like I can write something out, reiterate it. Maybe if
Okay.
I'll send you can take a look in them.
Yeah, so the important thing is they will clarify what are the pieces and the fact that we want quotes, right?
Mhm.
So this
Yeah.
is perfect. This is then I think we just want to change the structure here and see because again, if it's clear that he's saying this, and it's
Mhm.
clear that he's saying this, and then it's clear that Shankar says the opposite,
Yeah.
and we just need to say, look, these two things are different, and what he does is inconsistent with the literature.
Yeah.
That's it. So
Okay, yeah.
let's.
No, that sounds great. Yeah, I think I
Do you
was
think do you think you have enough, or you want me to look at the more of the details here? What do you want to do?
um no, I think this is good because it's kind of this is like subtractive editing, so I think
Yeah,
it's narrowed the focus even more, which
exactly. Yeah.
I think is appropriate. And then it's like you want it to be a letter to the editor.
If there is the option to do that, I'd rather do that
Okay, and the
because
editor of the journal that published his
they publish the response.
yeah.
Yes.
Okay, that makes
Yeah.
sense.
And so if we can, basically what I'm trying to do is to trim it such that, and I think we're going to be able to do it such that it's basically the 2 pages and that's it.
Mhm.
And again, with like the main thing being quoting Shankar. So
Yeah.
and don't change a single thing of the last paragraph.
Okay.
That's good.
Oh
Okay,
yeah.
so we close it like this.
Yeah, sounds good.
Okay. Anything
Um,
else people want to discuss? Otherwise, we call it a day.
I have nothing else.
And next week there is the school. And so I have no idea. I don't know that we're gonna do a live since we're basically gonna have like 6 hours of stuff, done. And
Mm.
okay,
well, it's
bye
looking pretty good.
everybody.
Thanks for
See you
having
next
me.
time.
Bye. Bye.